Here we have a pump pipe system where we have a pipe leading in that's pulling water from this very large reservoir down here. The inlet of the pipe is a distance little h from the free surface. Then water will go up this pipe through a 90-degree rounded pipe bend. We're given the equivalent length of that pipe bend. We'll come back to that a little bit later, but that's an expression of the minor loss in that pipe. And then it leads into a pump, which then goes into another pipe of a different length, and then it exits into the atmosphere, which is at a height capital H from the free surface. We're told we're dealing with water. We're also told the vapor pressure of water. This vapor pressure, by the way, would be an absolute pressure. We're also told that the pipe's made of concrete with a particular roughness of 3 millimeters, and we're given some of the dimensions. We're also given a pump performance plot, so we're given the head rise of the pump as a function of flow rate. Here it's shown graphically, but it's also given numerically down here. So this quadratic equation here, it's of order 2 here, that equation is the same as this curve. So it's given both graphically and numerically. We're asked to determine the system head curve for this pipe system, the operating point for the system. By operating point, I mean what volumetric flow rate will we actually be operating at? How will the flow rate within the pipe change over time if the pipe carries hard water and lime deposits form on the interior pipe walls? So let's talk about that a little bit later. Calculate the net positive suction head available at the pump inlet, and then if we want to add a valve to control the flow rate in the pipe, would it be better to put the valve upstream or downstream of the pump? So should we put the valve up here or put the valve down here and explain our answers? So quite a few things we need to get through. Let's go ahead and get started. So the first thing is to determine the system head curve for the pipe system. This is just a matter of applying the extended Bernoulli equation. So let's pick a couple of points. Point 1 will be at the inlet of the whole pipe system. So actually it's at the free surface. There'll be some streamline that'll go through the pipes and through the pump and then work its way to the exit here. So the system head curve should just describe the whole pipe system, which this one does. It goes from upstream of the inlet all the way to the outlet. I chose point 1 here because I know a lot of information here. I know the pressure is atmospheric pressure. I know the velocity is about equal to 0. I also know the elevation. Point 2, there again, I know the pressure, it's atmospheric pressure. The velocity is the same velocity in the pipe, and the elevation is also given. So those are good, convenient points to use, and we need something to describe the entire pipe system, so those 2 points do that. So let's write that down. The extended Bernoulli equation from point 1 to point 2. Write down the whole equation. And let's go ahead and write down some of the things we know. We said that the pressures at 1 and 2 were both atmospheric pressure. We know the velocity at 1 was about equal to 0. Velocity at 2 was just equal to the velocity in the pipe. I'll just call it V bar for convenience. Let's put a coordinate system. We'll say that Z is just right there. So that Z1 is just 0, and Z2 is at capital H. Notice point 1 is right at the free surface. It's not at minus H, actually. It's just right at the free surface. So we're going to just so Z1 is just actually 0 here. It's not minus H. So Z1 is equal to 0, and Z2 is equal to capital H. The HS is what we're trying to find. That's the system head curve. It's basically how much head rise the system needs from the pump in order to operate at the given flow rate. We also need to know something about the head loss. So the head loss will be sum of all the losses between points 1 and 2, multiplied by the velocity heads where those losses occur. So let's go ahead and write down what kind of losses we have. We'll have a major loss. So let me write that in the following way. Before I finish that, let me just go back up to the picture. We're told that the diameter of the pipe is 0.2 meters, so the whole diameter of both pipes is the same. So I'll just write D for that, but you'll see that we have 2 different lengths. So I'm going to write this in 2 different ways. I've got friction factor in the first pipe And there's so that's the major loss in that first pipe. And then we'll have the major loss in the second pipe. Notice that the velocity in each pipe will be the same because it's the same diameter throughout the whole system, so that we'll have the same velocities. If the upstream pipe, let's say the velocity up here, I'm sorry, the pipe up here had a different diameter than the diameter here, in that case the velocities would be different and we would actually have different velocities for these. But for the time being, or at least for this problem, the diameters are the same, so the velocities are the same. So those are the major losses in the pipes, and then we have the minor losses. So we have a minor loss due to, let's put this one in, we've got the inlet minor loss, that's called a reentrant inlet. We've got this minor loss due to the pipe bend. And then right at this point, we do not have an exit loss because our point 2 is right at the end of the pipe. So the velocity at point 2 is the same as the velocity in the pipe. We haven't lost any energy here. So at point 2, there is no exit loss. If we had made point 2, like, as the water came out and mixed with the fluid down here and then finally came to rest and we put a point 2 prime on the surface, then we would have an exit loss because we'd have dissipated all that kinetic energy. But when we put our point 2 here, it's not an issue. So we don't have an exit loss. So we'll need to include the inlet loss. It's a minor loss. So that'll look like that. And then we have our elbow loss. Okay, so let's go ahead and evaluate what some of these losses are actually. So the inlet loss we can look up from a minor loss coefficient table. If we do that for a reentrant inlet, this comes out to be 0.78. I just used the formula sheet to get that. The elbow loss is given in terms of an equivalent length of pipe. So the way that works is the loss coefficient is equal to the friction factor times the equivalent length of the pipe divided by the pipe diameter. This friction factor is the same friction factor as in the rest of the pipe where the elbow is located. LE is the 30. We were given that. If you go back up here, you'll see it says 30 pipe diameters. So this will be equal to 30D. Oh, it's a little crammed in here. Let me clean that up. So this is 30 diameters there. That's the equivalent length. And again, this friction factor will be the same as this friction factor. By the way, all three of these friction factors are the same because it's all the same diameter of pipe, the same roughness of the pipe, and it'll all be the same Reynolds number. Remember that the friction factor is a function in general of the Reynolds number and the relative roughness. And in this problem, since, oh, and by the way, the Reynolds number is the velocity in the pipe times the diameter divided by the kinematic viscosity. And since the pipe diameter is the same everywhere, we'll get the same velocity everywhere, the same diameter, same kinematic viscosity. So the Reynolds number will be the same in all the pipes, in both pipes. The relative roughness will be the same in both pipes because it's the same concrete pipe upstream and downstream in the same diameter. So that means that our friction factor will be the same everywhere. So if I write it a little more compactly, our head loss will be friction factor times the total length of pipe. That's just the L1 and L2. Actually, let me just write it as L1 and L2. L1 plus L2 plus the equivalent length of pipe for the elbow. The idea behind equivalent length is that instead of using a minor loss coefficient, the idea is imagine, so we know that if we have flow through the elbow, there'll be some head loss. Now imagine replacing that elbow with a pipe that has some length that gives a major loss equal to that minor loss. And that length would be called the equivalent length. So all of that looks like this. And then we just have the inlet loss. So all I've done is I've just taken this and just made it a little more compact. All right, and then what we can do is rearrange this equation to solve for the the shaft head we need from the pump in order to operate at the given velocity or volumetric flow rate. So if we rearrange our equation, our extended Bernoulli equation, so rearrange extended Bernoulli equation, we'll get the shaft head will be equal to the elevation head we have to supply plus our various losses here. So let me just, one other thing I guess I forgot to mention. The kinetic energy correction factor at 2, that's the kinetic energy correction factor right at the outlet here, I'm going to say is equal to about 1. I'm assuming that the flow is turbulent. I'm going to have to come back and double check that. But since the diameter of the pipe is about 20 centimeters, that's a pretty big diameter pipe. I expect that this flow will have a large Reynolds number and be turbulent. But I'll double check it when all is said and done. Okay, so when we rearrange that equation, we're going to get the following. Let me just write it all out. It'll look like that. So what this says is that the shaft head we need from the pump has to overcome the elevation head, because we're pumping the fluid from down here, and it has to make its way up here. So we're changing the potential energy of the fluid. So we have to overcome this elevation head, and we have to overcome all of the losses in the pipe. So we have this minor loss, we've got another minor loss here, and we've got the major loss in the pipes. So that's what this expression says, is the pump needs to supply enough head rise to overcome the elevation head and the head loss. And since we're told, well, we're going to ultimately find the volumetric flow rate, I'm going to just rewrite this velocity in terms of volumetric flow rate. So just remember that volumetric flow rate is the velocity times, let me rearrange how I'm writing this. Volumetric flow rate is the velocity times the cross-sectional area of the pipe. So that V bar is Q over pi d squared over 4. So we could take this and substitute it in there to put it in terms of volumetric flow rate. So let me just rewrite this one last time. Okay, so now we have our system curve. This is the system curve. What this means is, again, this is the head rise we need from our pump to go at that volumetric flow rate. Okay? Now, in order to find the operating point, so what we need to do is see where the system curve matches the pump curve. So this is what we need from our pump to go at that flow rate, but the pump can provide this much head at that flow rate. So we need to see where the two exactly balance, where the pump can provide just the right amount of head rise at the given flow rate to balance the needs of the system. Okay, so what we're ultimately going to do is take this pump performance curve, either graphically here or I'll do it in equation form, and set that equal to what we need for our system. So that's how we find the operating point. So let me just write the pump curve. All I'm going to do here is just repeat this equation. Okay, so let me just write that down. I think I've got it. Yeah, let me do that here. So this, if I'm just repeating it, it's 3.23 times 10 to the 1 meters plus 1.65 times 10 to the 2 second over meter squared times Q minus 4.82 times 10 to the 3rd second squared meters to the 5th times Q squared. So this is what the pump can provide. So at that given flow rate, this is what the head rise will be provided by the pump. This is the head rise we need from the pump for that given flow rate. So what we'll do is we'll just set these two things equal to one another. Okay, so we would have H plus all of this just a lot to write down, is equal to this. And rather than write everything down here, I'm just going to put dot, dot, dot. I think you get the idea. There's a Q and then a dot, 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 Q squared. And now you can see we'll have a quadratic equation in Q, right? There's a Q squared here, Q squared there, constant here, constant there, and then there's an extra Q. So we can end up solving for Q. Now before we can do that, if you go back and look at the numbers over on this side, if you were going to substitute in, you'll see that we're missing something. So we know K inlet, we know the diameter, we know G, we know the equivalent length, that's the 30 diameters. We know L1 and L2, those were given in the problem. I think L1 was 10 meters and L2 was 20 meters. What we don't have is F. So we need to find a way to figure out F. Now we said earlier that in general, the friction factor is a function of the Reynolds number and relative roughness. We know this from the Moody plot, right? Unfortunately, in the Reynolds number, there's a velocity. So this friction factor has a velocity buried inside of it, which makes everything complicated. But as you've seen in some previous pipe flow examples, where we're not given a flow rate or a velocity, you often have to do some iteration to find that velocity. But what we're going to do here is just make a simple assumption at the beginning. Let's just say that the flow is in the fully turbulent zone of the Moody plot. So assume fully turbulent, or it goes by different names, wholly turbulent or fully rough zone, so that the friction factor is only a function of the relative roughness. That means that the Reynolds number is large enough that it no longer is much of a factor. So if you calculate the Reynolds, the relative roughness, again, that roughness was 3 millimeters, and then the diameter was 20 centimeters, so you'd have to work out the numbers here. When you work those numbers out, this comes out to be 0.015. Let's go back to the Moody plot and see where we are there. So 0.015. So I'll go to my Moody plot. Here we are. Let me erase some stuff. This was from a previous example. Okay, so we're at 0.015, so that's right there for the relative roughness. So we're assuming that we're somewhere out here. So our critical Reynolds number here must be, greater than about 60,000. Right, so that's about 60,000. And the relative roughness, if we're in that fully rough zone, is about 0.044, let's say. Okay, so we're going to use 0.044 as our friction factor, and then we'll come back later and just check to see if we're above that Reynolds number. So let's go back to our problem. So from the Moody plot, friction factors 0.044, and now we have everything we need in this equation. So we now know our friction factor, and we can solve for Q. And when we do that, we'll get Q. Let's try that again. Q as our operating point comes out to be, let's see, got that worked out. That's 9.26 times 10 to the minus 2 cubic meters per second. And then if you find the velocity from that, that'll come out to be 2.95 meters per second. And if you find the Reynolds number from that, that comes out to be 590,000. So clearly, we're in the turbulent zone. So our assumption back here, where we assume the kinetic energy correction factor is equal to 1, well, that's easily satisfied. Furthermore, this Reynolds number of 590,000 was much larger than the 60,000 that would put me into the fully rough zone. So this assumption is also a good one. So everything is consistent. We're okay. That will now be our operating point. If this Reynolds number was less than 60,000, then in that case we would have to do some iteration. We would end up having to iterate to solve Q in this equation, where we would take into account the velocity dependence on the friction factor. So that's outside the scope of this problem, but we would have to do an iterative approach to solve for Q in that case. Okay, fortunately we don't have to do that, so we'll go ahead and continue on. So we now have our operating point. So 9.26 times 10 to the minus 2 cubic meters per second. Let's just go up here. 9.26, did I say? Let's just double check. 9.26 times 10 to the minus 2. So actually our operating point, if I look on this plot, we're somewhere way up in here. So we'd have to kind of continue this out. So we'd be somewhere up there. Okay, and let's now continue on with the problem. We've done those two parts. Now we're asking how will the flow rate change within the pipe over time if the pipe carries hard water and lime deposits form on the interior pipe walls. I don't know if you've ever seen this, but if you have like a cast iron pipe, when you first put it in, it'll be nice and smooth looking through the, looking down the pipe. But over time, what ends up happening is you get deposits lime deposits that will form on the walls, and so they'll start to get rough initially. In addition to lime deposits, especially if you're dealing with sewer pipes, then you get all kinds of nasty crud on here that decreases the diameter of the pipe. But at least for the freshwater pipes, you'll just get lime deposits. Ideally, you don't get any crud other than possibly rust and lime deposits on the interior pipe wall. So the walls of the pipe are going to be roughened. And so the question is, what happens to the flow rate in those conditions? Well, and we're also told to assume that the deposits don't significantly affect the pipe diameter. So it's kind of like the picture I've shown here. It's just rough walls, but the diameter doesn't change very much. So in that case, we can just kind of visually or graphically show you what's going to happen. So let me do that down here. So here's our head rise versus volumetric flow rate curve. Let's say this is our pump curve. And then our system curve looks something like this. It'll look something like that. And our operating point, of course, would be right there. It's where the two match one another. That's exactly what we did. What I've shown here graphically is exactly what we did right here. This was our system curve. You can see that that's a parabola that has kind of a positive curvature. It's curving upward because everything is, there's an intercept here, and then it goes positive, so it's headed upward. And then for our pump curve, you can see it actually is a quadratic also, but there's a negative here, so it's the curvature is negative. That's why it's headed down. And then we solve this numerically, but here I just kind of show it graphically where the operating point is. So anyway, now what we're saying is that there's more roughness in our pipe. So that shows up right in our friction factor in our analysis for the system curve. Right, so this is where the roughness would show up here. Remember that the friction factor is a function of the relative roughness. So if epsilon gets bigger, if you think back to the Moody plot, what will happen is the friction factor will get bigger. So larger roughness, let's go back and just kind of show that. So if you go to the Moody plot, here's where we're starting. But if we have a larger roughness, let's say we go to 0.00 or 0.03, you'll see that friction factor is higher than what we started with. So the F value gets bigger. Okay, lots of back and forth. So since the F value is bigger, what you'll see is that this term in front of the Q squared will get bigger, so we'll have a steeper curve. It starts at the same intercept, but the curve will get steeper. So what will happen is it'll look like this. So system after deposits Now the pump is unaffected, so the pump will continue just to be like that. And so you'll see now that our operating point will actually decrease. So our new operating point is a little bit lower because our where it crosses the pump curve is in a different location. So that's what happens when you start getting lime deposits in your pipe, is that the operating flow rate will go down. Okay, so that explains that part of the problem. Hopefully you understand all that. Okay, now we're asked to find the net positive suction head available at the pump inlet. So to find that, what we're going to do is apply the extended Bernoulli equation from point 1 now to the suction side of the pump. Let's just call it point S for the suction side of the pump. And then we'll rearrange that extended Bernoulli equation to give us the net positive suction head available. So let's do that down here. So the extended Bernoulli equation, I'm going to stick with the blue color because I think it looks nice. So we're ending at the suction side. We're starting at the same point. There's our extended Bernoulli equation. There's no pump between points 1 and S. Remember, the pump is downstream of the suction side of the pump. So it's not between point 1 and S. We still have P1 is P atmospheric. We have V1 is still about equal to 0. Z1 is still equal to 0. It's right on the free surface. Z on the suction side is equal to capital H. If you go back up to the picture, sorry, we're going back and forth so much. But the suction side right here is still at capital H. Again, point 1 is at 0 elevation, still atmospheric pressure. Now the head loss term will include the reentrant inlet head loss, the minor loss due to the pipe bend, and just the major loss due to this L1 length. We don't worry about L2 because it's downstream. It's not between point 1 and S. So we'll just have that for our major loss. So let's write that down. So head loss between 1 and S, I should say. By the way, I made a mistake here. Those should be 1S. Same here. So we'll have the major loss times L1 over D. We'll have the inlet loss. And then we'll have the elbow loss in terms of equivalent length. All right, and we know all of these values. The friction factor we found just a little while ago, it was right back here. It's the same friction factor. We know L1, we know D, we know the inlet minor loss coefficient, we know the equivalent length. We know everything here. Let's rearrange the equation to put it in the form of the net positive suction head. And this is actually the net positive suction head available. We're doing this analysis for the pipe system. So this is what our definition of net positive suction head looks like. So I can rearrange this extended Bernoulli equation to make it look like that equation. So here we'll have minus ZS, or that will just be minus H. ZS, remember, is just equal to H. And then we have our minus... actually, I take that back. No, this is correct. I've got it right. And then we have our head loss term, so that'll just be F times L1 over D plus K inlet, F times LE over D, V bar squared over 2G. Make sure I've got this all written correctly. So far so good. The only other thing I'm missing is the vapor pressure head. So that goes over on this side. Somehow I think I've got a sign incorrect. So let me just make sure I've got this all written correctly. Oh, I know what I did. I know what I missed. What I missed was this pressure P1. I have to include that. That's right here. So this will have a P atmosphere all over rho G right there. Sorry for cramming that in at the end. I just forgot it. There. That's what we have. So there's P atmosphere minus the elevation head, minus some head loss, minus the vapor pressure head. So we can go ahead and plug in values. We know all the values on this side. One thing we have to be careful of is let's use an absolute pressure for the atmospheric pressure because we're using an absolute pressure for the vapor pressure. The vapor pressure was given in the problem statement right back up here as an absolute pressure. So we just need to make sure we use absolute pressures everywhere. So when you plug in those numbers, you'll get NPSHA comes out to be, let's see what the value is, 6.16 meters. So that's what our net positive suction head available is. So we would want to make sure that our net positive suction head required is less than that 6.16 meters in order to avoid cavitating in our pump. Okay. And we don't know whether it's going to cavitate or not because we weren't given the NPSHR curve for our pump. We were only given the head versus flow rate curve. All right, the very last part of this problem is, would it be better, okay, so we've done this part. Now the last part is, if we're going to add a valve, would it be better to put the valve upstream or downstream of the pump? So do we want the valve somewhere up here or somewhere down here? So let's first think about what happens if we put it upstream. Okay, if we put it upstream of the pump, how that affects things. So if we put it upstream of the pump, then there'll be another minor loss in front of our pump. So when you go to the NPSHA curve, or expression, sorry, when you look at this expression for the NPSHA, we'll have another minor loss. So there'll be an additional term here that subtracts from our NPSHA. So that means our NPSH available to the pump will actually be smaller if we put the valve upstream. And that makes it more likely that we're going to cavitate our pump because this number will be smaller and we have to keep our NPSH required less than that. So it gives us less room for the pump. So we really don't want to remove any NPSH A from our system. It means we're more likely to cavitate the pump because it'll subtract here as a minor loss. So really we'd be much better off putting the valve somewhere down here. So putting a valve here at the outlet would be much better because if you do that, then you're not going to cavitate your pump. Since this minor loss is downstream of the pump, it doesn't impact the NPSHA available to the pump because that's just when we do that calculation, it's just for all the upstream stuff, not anything downstream of the pump. So for that last question, we're better off putting the valve downstream of the pump in order to be less likely to cavitate our pump. Okay, so I think that does it for the example. We've covered a lot of different things. Hopefully it all makes sense to you. So we'll just go ahead and end it there.